Welcome to this week's tutorial. In this week, we will be looking at few more applications of direct product. So let us see what kind of questions can come in direct product applications, what kind of problems you can encounter in direct product applications. So let's start tutorial 8. So let's try to solve at least two questions. So let's say in later part of this course, we'll be looking at introduction to spectroscopy. So this application is in spectroscopy, as we have also learned in the regular class. So let's say somebody wants to record vibrational spectra. Don't worry about what this spectroscopy is and what is the use of this spectroscopy. We'll come back to it later. But let's say if we are interested in recording vibrational spectra of staggered ethane, and maybe another molecule is any other molecule with square pyramidal geometry. So now we want to know whether the vibrational spectra will come in these molecules or not. And so to know this, the kind of integration that we need to solve is of this form. And do not worry about how this integration comes in, but let's directly look at the application part. So this is the kind of integral that we need to solve. If this integration does not go to 0, we will see vibrational spectra. If this integration goes to 0, no vibrational spectra, right? So this together is called as selection rule. All right. So now let's say the question is given that psi v0 belongs to totally symmetric representation. And f belongs to x, y, z, x, y, y, z, z square, y square, x square, zx, or any combination of these, or sets thereof. Okay. So these two things are given. So psi 0 is totally symmetric representation. F belongs to any of these functions. That means the basis set of this function is known. Now we know that this is totally symmetric representation. Now the question is asking that what would be psi v1 so that I does not go to 0. So now you try to remember under what conditions the I does not go to 0. What are those conditions? So the direct product of all these three, direct product of, let's say, FA, FB, FC must contain totally symmetric representation for I is not equal to 0. Remember that we have studied this, right? Alright. So now we have to find out what will be your psi v prime for these two are given to you under these two different point groups. Okay, so the first point group is staggered ethane. So staggered ethane, we must know what is the point group of that. So staggered ethane belong to D3D point group. Again, we have discussed this, so I'm not going to discuss this again. So now let's try to find out what is the character table of D3D. Okay, we'll see what we have to read out of the character table. So I'll just write down the character table of T3D. Let me take a look at so what we have here is E 2C3 3C2 I 2S6 3 sigma Ds, right? And we have A1G, A2G, EG, A1U, A2U, and EU. Now we have totally symmetric representation, so all ones. A2G will be 1, 1, minus 1, 1, 1, minus 1. EG will be 2, minus 1, 0, 2, minus 1, 0. And we have now 1, 1, 1, minus 1, minus 1, minus 1, 1, 1, minus 1, minus 1, minus 1, 1, 2, minus 1, 0, minus 2, 1, 0. Now if you look at these two areas here, so you have the basis sets written here. So my basis set here is RZ, RX, RY. Then I have Z over here, XY. Then I have X square plus Y square as well as Z square. Then I have joint representation for X square minus Y square comma XY as well as XZ, YZ, right? So these are my basis sets. Now I know that my psi v0 is, so I is equal to psi v0 f psi v1 d tau. Now psi v0 is a1g. It is given that it is totally symmetric representation. F now can belong to any of these combinations with x, y, z, x square, y square, z square. So it can be a1g, it can be eg, it can be a2u. Now our job is to determine psi v1. Now it is very simple. So psi v1, whenever f is a1g, it has to be a1g. Whenever f is eg, it has to be eg. Similarly a2u. And so why is that? Because now if I take a direct product of these three, this will be a totally symmetric representation. If I take a direct product of eg into eg, this will contain a1g. If I take a direct product of a2u into a2u, this will be a1g. Similarly, EU into EU would also give you a totally symmetric representation. Remember, this thing comes from that direct product of two same irreducible representation will always contain a totally symmetric representation, and we want totally symmetric representation. At least one of the components has to be totally symmetric representation. So the only combinations where I will contain totally symmetric representation will not go to 0, others will all go to 0. So combinations of psi v1 as a1g, eg, a2u and eu will only give a1g, and that's how these will be your correct answers. Okay, so psi v can belong to any of this, and only then it will give you non-zero I, and hence the vibrational spectra of staggered ethane will be visible. So that is one. Now let's see the same case for square pyramidal molecule. So square pyramidal is C4V point group. So again, for C4V point group, we need to first write down the character table and then look at the basis sets. So I suppose this should be easy, but let's just do it for completeness. E 2C4 C2 2 sigma V 2 sigma D, and this side I have A1 A2 B1 B2 E, and here I have all ones totally symmetric, and here I have 1 1 1 minus 1 minus 1. Now the most important part is to look at the basis set areas. So this will be Z, RZ, and here it is X, Y, RX, RY, X square plus Y square, Z square, X square minus Y square, XY, XZ, YZ. Now here my integral is again of the same form, psi v0 f psi v1 d tau. Now I know that psi v0 is a1, totally symmetric representation. Now what are my f's? What are the possibilities for f's? So f can take value as a1 because of this, then b1, then b2, and so that means my psi v1 will also be of these forms. That means the basis for psi v1 can be a1, b1, b2, and depending on what is the actual function, accordingly the psi v1 will have different basis sets, right? So these will have non-zero I, because this direct product will contain totally symmetric representation, right? So this should be very, very clear. So now let us look at one more example, one more question, one more application in direct product. So the question reads like this. So in connection with certain form of spectroscopy, again it's a spectroscopy related problem. So in connection with certain form of spectroscopy, which is a circular dichroism. If you have not learned about this, you will learn it later, and I mean not in this course though. Magnetic circular dichroism. So it is necessary to know what electronic transitions are magnetic dipole allowed. What electronic transitions are magnetic dipole allowed. So we have already learned which transitions are electric dipole allowed. So this one is about magnetic dipole allowed, right? So in this case, the transition dipole moment will be of different nature. Now the operators for this have the symmetric properties. This is another way of saying that the basis of this operator. Symmetry properties of Rx, Ry, Rz. Okay. So now the question part is, for a molecule with tetrahedral symmetry, TD symmetry, TD point group, determine which pairs of states could be connected by a magnetic dipole allowed transition. So now they are asking that if the operator for this have the symmetry properties as Rx, Ry, Rz, now for a molecule with TD symmetry, let's say methane, determine which pair of states could be connected by a magnetic dipole allowed. So when they are asking which pair of states, that means they are asking that what will be the symmetry of those states which can be connected by a magnetic dipole allowed transition. So the first thing first is to set up integral for this. So integral will be the same. So you want to see under what conditions the integral will not go to 0. So psi 0 mu psi 1 d tau. Now in this case, we don't know what is psi 0. We don't know what is psi 1 because we want to calculate the pair of states. These are the pair of states. Remember that these are the functions which describe the states, right? Psi 0 and psi 1. So we don't know what is psi 0 and what is psi 1, or what is the symmetry of psi 0 and symmetry of psi 1. So we want to calculate that. And given is that mu has symmetry as Rx, Ry, Rz. Okay. Now we want to choose psi 0 and psi 1 so that the overall direct product of this does not go to 0, because it has to be connected by a dipole, magnetic dipole allowed transition. So that means I should not go to 0, right? Now let us look at the character table. Maybe let's go to next page. So let's look at the character table of TD symmetry. So tetrahedral point group. So we have E8C3, E3 6S4, 6 sigma Ds, and you have A1, A2, E, T1, T2. So you have all ones. Then E2 will be 3 ones and 2 minus ones. And you have 2 minus 1, 2, 0, 0. 3, 3, 0, 0, minus 1, minus 1. Now is the interesting part which you want to focus on. Rx, Ry, Rz, and this is my x, y, z, x square plus y square, although it is not required to see this one now. E is 2z square minus x square minus y square. Okay. So now the question is saying that mu has the symmetry of T1. Mu has the symmetry of Rx, Ry, Rz, right? Now psi 0 and psi 1, we don't know. Now we have to take a direct product of psi 0, mu and psi 1 so that the overall thing contains totally symmetric representation, right? So now what are the combinations which are possible? So you have psi 0 T1 psi 1, right? This is my integration. Now we know mu, so I have put T1 over here. Now what are the combinations for which psi 0 and psi 1 can be put over here, so that the overall direct product, triple product of this will not go to 0. That means it should contain totally symmetric representation. So I can choose this as A1, T1, T1. That is my first possibility, because now I know that if this is A1, it will not matter. The direct product of this will not change upon multiplication with A1, because A1 is all ones. So T1 into T1 must contain A1, right? So overall it will contain A1. So this will not go to 0. Then what else? Now the other possibility is T1 is constant. T1 I cannot change. Now the other possibility is if I create another T1 by multiplication of these two, right? How can I create another T1 by multiplication of, so it has to be a one-dimensional and another three-dimensional representation. So that means it has to be a T2. Now if I combine T2 into A2, what do I get? So 1 into 3 will give me 3, 1 into 0 will give me 0, 1 into minus 1 will give me minus 1, minus 1 into minus 1 will give me plus 1, minus 1 into 1 will give me minus 1. So that means if I multiply A2, if I take a direct product of A2 into T2, I will get T1, right? So that means again I will have a situation where direct product T1 will come. So this combination will also not go to 0. So that means there are two possibilities which will not go to 0, at least by just looking at it, right? Rest of the possibilities, I would ask you to do a home assignment. You've got the concept, right? If there are any more combinations that makes I not equal to 0. Combinations of psi 0 and psi 1. So these are the two possible combinations that I have just told you by just using the direct product rules. But you can take different combinations. You can place different IR irreducible representations here and see the triple direct product, whether it contains totally symmetric representation or not, and accordingly tell what will be the answer. So the idea is, once you know how to deal with direct product, you can solve a large number of spectroscopy based problems, right? So that is all for today. So let's look at symmetry adapted linear combinations, more problems into that next week. All right, thank you.